We will now start Module 2, Lesson 11. Please open up your math binder and turn to Module 2, Lesson 11. Please open up your math notebook and prepare to take some notes on this lesson. So our aim today is, what does it mean when figures are congruent? Well, let's give a definition, and this you need to copy in your notebook. Congruence is the sequence of basic rigid motions that maps one figure onto another. And a sequence to show congruence can be any combination of the three basic rigid motions that we already know: a translation, a rotation, and a reflection. It can use all three, or just two of them, or even just one of them. Another way to say that two figures are congruent is if there's a sequence of rigid motions that maps figure S to S prime, or the congruence of S is equal to S prime, or S is congruent to S. The symbol that you're seeing is the symbol for congruence. This symbol right here is the symbol for congruence. So if there is a congruence so that the figure S is equal to S prime, and if is there also a congruence that says S prime is congruent to S? So you're probably thinking yes, but let's do an example so we know this for sure. So in this picture, you see two figures on the left with a line of reflection L and a figure on the right that's called S prime. And then there's a vector Mn. So let's see what happens. We're going to translate figure S along vector Mn. And I have a transparency like image. And I just translated it to figure, the second figure. Now I'm going to reflect over the line of reflection and line it up. And it is a little disconcerting because you're seeing the same image on both sides, but you could do this yourselves. And if you notice, this figure right here was originally the figure that was over here. We translated it up, then we reflected it, and it wound up over here. So what happens if we do this in reverse? So let's reflect this image here. And then let's translate that figure across vector NM. So we're going the opposite direction. And you see it does map onto it. So this shows us, and if you're not convinced, then you should draw these very simple figures. Draw S, draw a vector, Mn, translate your figure across the vector, have a line of reflection going straight up and down, a vertical line of reflection, translate it, then reflect it over that line, then reverse that. Reflect it over the image you got on the right side, reflect it over the line of reflection, and then translate it back. And it's kind of obvious that it will wind up in the same place. So what this is telling us is that by performing a translation followed by a reflection, it can be undone by reversing the order. So this really is showing us that if figure S is congruent to S prime, then S prime is also congruent to S. So we're going to try the same reasoning and see if it works for rotations. So you're going to try example number 1 in your binder for lesson 11. There are 2 examples. You're going to do the first one. So pause this video and follow the instructions for exercise 1. Now that you've finished A, B, and C, let's go over and review A. If you haven't done A, B, and C, please pause the video, and please complete A, B, and C. So the first one says, describe the sequence of basic rigid motions that shows S1 is congruent to S2. Well, what we want to do then is map S1 onto S2 using a series of basic rigid motions. So what you should have drawn is a vector, and this shows it right here, vector AB, and you translated S1 along vector AB, and then you would perform a rotation of d degrees, and then what you could have done is, once S1 is rotated d degrees, it should line up like this. Sorry for the drawing, it's a little difficult to draw on this iPad, but and then you would reflect over the longest side of S2. So we would do a translation along vector AB. We would do a rotation around point B of d degrees so that the sides of those figures are right next to each other. And then you would do a reflection across the longest side of the S2 so that S1 maps to S2. Then the translation S1 followed by the rotation followed by the reflection equals S2. You should have this written in your notes the way it exactly is stated here. You're saying in words exactly what you're doing with your transparency. You're translating it, then you're going to rotate it, and then you're going to reflect it. And S1 should be laying right on top of S2. Part B says, describe the sequence of basic rigid motions that shows S2 is congruent to S3. So here, you could have drawn a vector from B to C, from point B to point C, and translated it along the vector. And S2 would now be this dotted figure. And then if you rotated it d degrees about point C, S2 would map nicely onto S3, which means then the translation of S2 followed by the rotation equals S3. The last one was to describe the sequence of basic rigid motions that shows S1 is congruent to S3. So this takes a little bit more time because you're moving it across the plane. So you could draw a vector from point A to point C and translate it and get this dotted figure here, S1. And then you could rotate it d degrees so that the longest side of the figures are laying on top of each other. So they're mirror images of each other, and the longest side here is lying on top of the longest side here. And then reflected over that longest side so that S1 would map onto S3. In other words, let there be a translation along vector AC, let there be a rotation around point C of d degrees, and we're rotating in a counterclockwise direction. Then let there be a reflection across the longest side of the figure so that S1 maps onto S3. So then we can say the translation of S1 followed by the rotation followed by the reflection equals S3. All of this you should be doing with your transparency and then translating what you did with the transparency into these types of words so that you're clearly explaining what you are physically doing. So now the next question is, was all that work necessary to show that S1 was congruent to S3? Well, hopefully you realize the answer is no, because we know that all those, a translation, a reflection, and a rotation preserve angle, measurement, segment length. And if we know that S1 is congruent to S2, and S2 is congruent to S3, then it should naturally follow that S1 is congruent to S3. Since sequences of basic rigid motions have the same basic properties as individual basic rigid motions, we can also say that congruences also maintain these same basic properties. In other words, so given that sequences enjoy the same basic properties of basic rigid motions, we can state three basic properties of congruences. A congruence maps a line to a line, a ray to a ray, a segment to a segment, and an angle to an angle. This was true of basic rigid motions and sequences. A congruence preserves lengths of segments, and a congruence preserves degrees of angles. Exactly the same thing as we said for basic rigid motions and sequences of basic rigid motions. So now pause the video, and I want you to do example 2, exercise 2, sorry, and then when you're finished, turn on the video. Okay, for this exercise, they basically wanted you to perform, they told you exactly what to do, a translation followed by a rotation of figure XYZ, where T is the translation along vector AB, so you're sliding this, you're using your transparency, and you're sliding this triangle from A to B. So you're drawing your figure, you're drawing point A, and you're sliding your transparency up to B. And then you're rotating it about point O. You choose the degrees, but you'll wind up, you should stop when XYZ, stop somewhere where you're comfortable, where you can write X prime, Y prime, and Z prime. And then you're going to label that transformed figure X prime, Y prime, and Z prime, like I did here. And then the question is, will XYZ be congruent to X prime, Y prime, and Z prime? Well, you should see that they are congruent. You took the same figure, and you just translated it and rotated it. Nothing else changed. So they are congruent. So you should now definitely be convinced that a sequence of basic rigid motions maintains the same properties as individual basic rigid motions. And then to summarize, please read the lesson summary on page 61. Pause the video while you do that. So now we have a summary for the lesson. We now have a definition of congruence. We now have a new notation for congruence. It's the equal sign with the squiggly line on top of the equal sign. And you know that the properties that apply to the individual basic rigid motions also apply to congruences. So please be prepared with questions on lesson 11 when we meet again. This concludes lesson 11.